For the my undergraduate degree, I took information rate connected galaxies MaNGA project under supervision of the professor and others in team. So, in a general way, galaxies are gravitationally bound systems composed mainly of stars, gas, dust, and dark matter. Most of the galaxies have a supermassive black hole in their center, but only just a few fraction have an energetic phenomenon in their nuclei composed of a supermassive black hole accreting matter. And this phenomenon is called active galactic nuclei, or AGN. The matter created by the black hole tends to form an accretion disk, and some charged particles in this disk tends to create a magnetic field that interact with some particles with relativistic velocities. And this interaction tends to result in jets that can influence in the whole of galaxies some properties of the whole galaxies, just like star formation. We have some evidences that the gas, the jets, and the AGN itself can both can heat and can remove the gas of the whole galaxy, suppressing the star formation. As well as we have some evidences that the AGN can create a rich environment that boosts the star formation in the whole galaxy. So the goal of my work is to search for observational evidence of how the AGN can affect the stellar population in its whole galaxy, obtaining star formation rate for the AGN control period to star formation synthesis. It means that we will compare star formation rates in active galaxies with inactive galaxies. And also obtain the star formation rate surface density for the AGN control period near the nuclear region. To achieve this,
What means to do this?
one AGN, two neutral galaxies. So to achieve this, we use the MaNGA survey, which observed approximately 10,000 of galaxies in the local universe, with the main goal of obtaining the climatic structure and the gas composition of the gas. And the main advantage of the MaNGA is that it uses favorable spectroscopy. So we have a data cube, and we don't have just one spectrum for each object. We have a lot of spectra. So it means that we can have a more detailed study of each object. And to investigate the effect of the AGN in the whole galaxy, it's very important to define a control sample. And our control sample is composed of two inactive galaxies matched to each active galaxy. And they are similar in morphology, redshift, stellar mass, and inclination, being possible for more than one active galaxy to share the same control galaxy. Galaxies as being active or inactive use the BPT and the one diagnostics diagrams. So the BPT uses the line fluxes, the radius of the line, the emission lines O3 to H beta, and N2 to H alpha to classify the galaxies. And the one diagram uses the equivalent bit of the emission line H alpha and N2 to H alpha. So for a galaxy to be classified as being active, it needs to be in the safer or minor region in both diagrams. It means that it needs to be in the AGN region. But for a galaxy to be classified as control, it needs to be in the star forming or in the transition or in the line region in the BT, and don't show signs of AGN ionization in the world. Classified 293 active galaxies and 586 control galaxies. And to investigate the dependency of the luminosity of the AGN in the star formation rate, we classify the active galaxies in three luminosities: low, intermediate, and high. The information about the stellar populations, we use the starlight that perform the stellar populations. That is basically a synthetic spectra under the observed one, and through this, it obtains some properties about the stellar population, like the mechanicity, the historical of the star formation, and the star formation rate for a certain interval age of the population. In our case, we use an interval of 20 million years old. So, through the stellar population synthesis for the age of population, we obtain the star formation rate for the active galaxies and both controls. Here we have a map of the star formation rate for a galaxy with intermediate luminosity. So we can see here that the active galaxy has a higher star formation here at the core and some spots near the corners. In the controls, we have some empty spaces in white, and it means that we don't have information about the 20-meter-old population in this region. We have a higher star formation in the nucleus as well. But the star formation rate is not necessarily what we want, because if we obtain the star formation rate in galaxies of different sizes, maybe we'll have a false result. So what we do is to divide the star formation rate by a certain area, and this area is an area corresponding to a radius of 2.5 arcsec. That is the minimum angular size that the instrument of the MaNGA can analyze the low source. So, dividing the star formation by this area, we obtain the star formation rate surface density. And here we have a map for the same galaxy of before. And looking at this map, we don't have so much clue about what is happening in these galaxies. So, we chose the logarithm of the sigma SZ R of the AGN under the sigma SZ R of each control. So if you have a positive, it means that the active galaxy is forming the stars. But if the result have negative, the control galaxy is forming. And we made a history of this, and we can observe that the positive interval is a little bit bigger than the negative one. But transforming into numbers, we obtain that the active galaxies are forming more stars than the control galaxies, 5 times higher. And in terms of percentage, we obtain that 62% of the active galaxies are forming more stars than the mean and the standard deviation is also shown, and the mean is the mean of each interval. Of luminosity, we obtain a certain pattern. We obtain that 55% of the AGNs of high luminosity are forming more stars in control. 60. And 57% of the active galaxies of intermediate luminosity are forming more stars. And 52% of the active galaxies of low luminosity are forming more stars than the control. The mean and the standard deviation is also shown. As a conclusion, we obtain that the active galaxies sample to be a higher star formation rate density compared to the controls, and that the active galaxy contributes to star formation. In terms of luminosity, we obtain that more luminous AGN is a bit higher star formation rate surface density compared to the controls. And since the AGN luminosity is a tracer of the nuclear activity of the AGN, we conclude that greater nuclear activity means greater gas viability. It means that the AGN is turning the environment for which to form stars.